13 of the lecture notes, and I think this may be chapter 15 in Nova's book. And the subject is second quantization and the quantization of the Schrodinger wave field. So you've already seen how to quantize the classical field, right, the electromagnetic field, or crystal vibrations of a crystalline lattice. Now today we're going to talk about how to quantize the Schrodinger field. And for today we're going to work with the fermion case. So I'm going to show you how to construct the wave function operators and what the wave function operators mean. And then we're going to talk about how to interpret the wave function operators in terms of a particle density, a local particle density function. And then we can talk about constructing operators as you would do in ordinary quantum mechanics. How do you write down operators in a second quantized form? And then if we have time in the end, I'd like to recap, do something we didn't have time to do in the previous lecture, which is magnetic flux quantization. But let's see if we have time for this today. Okay, so let's review some of the basic stuff. You've seen how to quantize a classical field, and in the quantization of the classical field, there was an important concept called the occupation number states, or the Fock state. Right. So how do we write down a state in the Fock state representation? Instead of writing the state of every particle, what we write is we have some ket, and in there we just label the occupied states. Maybe the m's and the nth state are occupied in this case. So this is the occupational number state. And what do we mean by m and n? It means that we have some operator. Okay. So maybe this operator is a operator A. Okay. And it has a complete set of eigenkets. A n is equal to A n. Right. So we start with a complete set of eigenkets, and we basically construct a direct product space with them. Right. We put them together in this form, and this form is the occupational number state. In the fermion case, we know that there's a Pauli exclusion principle which stops there being more than one particle in one state. So in the fermion case, the Fock state representation is very simple, because there's no ambiguity as to how many particles there are in the state. There can only be one. So we just write down the occupied states and not write down the unoccupied states. So let's go with this two particle example. So maybe I start with a two-particle example. The m and the nth state are occupied. Now I'm going to, we know that the correct two fermion states will have the requirement of antisymmetry under exchange. Right? So let me impose that by saying in my notation that this is equal to minus m. Okay. And you'll see that everything about the fermions, the statistics of the fermions, comes from this antisymmetrization requirement. All right, so now let's define particle creation operators. Let me just say creation operator. And these creation operators are labeled by a state. Let's say that we use B for the fermions. So, and we're going to call the creation operators with a dagger. And this is in analogy with the classical field case where you have the A dagger creating a quantum of energy for the field. And let's label it with the case state. So we're going to define this operator, and its action is going to be when this acts on some two-particle state. And let's say for now that K is not yet in here. So this is going to take us into a three-particle state, and it creates a particle in the case state. And because we have seen that the order of these m and n matter, so we will require that when this creation operator sees this state, it's going to create a particle at the first place. Okay? So this is to respect the order of these numbers, right? So okay, so this is the action of the creation operator, and this is by definition. So we define this. Okay. So now let's consider a sequence of creations. So we can consider creating the particle in the L state and the case state in sequence. This is going to give you which is equal to K, L, M, N, correct? Okay. And now if I reverse the order, obviously I'm going to get LK, M. So what we found is that because these two are related by this exchange antisymmetry, so we find that in general, is this correct? Acceptable? So I can write this as minus K, L, M, N, right? So now if I sum the two, sum this and this, we have a cancellation on the right-hand side, right? And then because these M and N that we started with were arbitrary, we only require that, we don't consider the trivial case where the K and L states are already occupied. So now it must be that this be 0. So now you've seen the commutator of two operators, and that's with a minus sign. This is called the anti-commutator, and there are several notations for it. The one that's probably the most used is using this curly bracket. Okay. Alternatively, you could also write the square bracket with a plus sign here, indicating that it's anti-commutator. Okay. So now we have placed a dagger here. Let's take the Hermitian adjoint of this, the Hermitian conjugate of this equation. So when we take that, we're going to switch the order of the operators, and then change just remove the daggers. Right? So we get that BL. So we have found that the Hermitian adjoint is also anti-commute, like this. Okay. But what is the action? What is the action of these operators without the dagger? Okay. To see that, let's consider an inner product. Let's consider the normalization of the state. So we require that K, L, M, a state like this. Okay, and this can be any three index. K, L, M. We require this to be 1 so that the states are correctly normalized. Right? Okay, but there are two ways to interpret this. So I can write K, L, M, and this, I can change this cat to the creation operator of the K state operating on the two particle states. Okay. This is certainly true. So now, let me take the adjoint of both sides. Okay. So if I take this, 1 doesn't change. Right? So now let me take the adjoint of this thing here. So this changes to L, M, B, K, K, L, M is equal to 1. Okay. let's group this operator with this cat over here, so that it operates on a cat. So the action of this this BK operator, because of the normalization requirement, must be that it destroys a particle in an already occupied state. So this is equal to L. So it reduces the particle number in the K state by 1, and because we have fermions. You either now since we started with a state in which this is already occupied, if we started with say the L and M state, then we know this is 0 because there's nothing to destroy in that state. Okay. So now, this is the action of this annihilation operator. So we call these operators without the dagger the annihilation operators. And their interpretation should be quite straightforward. So now let's consider the product of creation and annihilation operators. Okay. So I'm going to consider products like these. B K dagger B L and also B L B K dagger. So we want to test the action of these operators and see if their order matters. Right? So that means we're seeing if we can just take these two across each other. Okay. So let's think about a state that we need to work with in order to see the action of this. Because we're destroying the L state here, we need a state in which L is already occupied for it to have non-trivial result. Right? And then we need a state in which K is not yet occupied. Okay. So let me go with a state, a 3-particle state, L, M, N. Okay. Now, when these two applies here, we're going to have non-trivial results. Right? So let me do this. The first one, now this destroys the L and creates a particle in the K state, all in the first position. Right? So this is equal to K and N. Right? But if we reverse the order, okay, we're going to create a particle in the first state first. In the first position first. So this gives you K, L, M, and N. Now, in order for this to destroy it, you first need to change the state and move the particle to move the state to be destroyed or annihilated to the first position. So that amounts to using the anti-symmetry requirement to pick up a minus sign. And then now this can readily destroy a particle in this position at this state, right? So this is equal to minus K. And we're thinking about the case where K and L are not the same. Okay. So now we can conclude based on these algebra that in the case where K and L are not the same, this is clearly 0, right? Because again, we pick up a minus sign if I add these two states, it's 0. But what about the case when K and L are the same? Right? So when K and L are the same, let me do the algebra again. So let's think about this acting on a state in which K is not yet present. Okay. So if that was the case, then we know that this is going to give a 0 result because the K state is not yet present. So maybe this acting on the Mn state will give me 0, while this acting on the Mn state, well, it's going to create a particle in the first position and then immediately annihilate it. So this is just the original state, right? Yeah, right. Okay. Now, alternatively, if we work with a state in which the k is already present, then we see that this will give us the result of the same thing as an identity operator, and this one will give us 0, because we cannot create two particles in the same state. Right? What this means is that, in general, this is always the identity, because either this is going to act on a state with k already present or not, right? Okay. Now, what about so far we have only considered simple cases where the k is already in the first position for us to destroy or create. What about if I started with a state like this, m and k, or if I have a bunch of particles and the k state that we need to work with is, say, in the ith position. Okay. What do we do in this case? We just use the anti-symmetry requirement. Right? We move the k I times, and by moving the k I times, you pick up a factor of -1 to the ith power. And whether you are going to, and when we're working with these things, whether you're going to create one or destroy one. In the case when you need to destroy one, you need to move this out. So you require that this is equal to -1 to the ith power k, etc. Right? So you acquire this factor. Now, in the case where k is not already present, then you create a kth particle. But to get this state, you need to move the kth particle. You need to move the k state inside I times, right? To move to the ith position. So once again, you pick up this -1 to the ith power factor, right? So actually, it doesn't matter where the k state is. Okay. So we conclude that this is true. Now we can combine these two by saying that this is equal to, well, this is for k not equal to L, and this is for k equals to L. So now let's combine the commutation relations of these creation and annihilation operators for the fermion case. So the anti-commutator becomes important here, and we conclude that this is 1. Okay. And we can use these simple commutators to construct more complicated ones with products of more than 2 terms. Okay. But these are the basics. All right. So these are the commutation relations for the fermion case. For the boson case, well, we basically just replace some stuff with the commutator and replace B with A. But we'll get to that later. So now, let's move on to the next topic, which is the wave function operator. So far, by working with the Fock state, the good thing about working with the Fock state is, since the Fock state has this, the notation already takes care of this anti-symmetry requirement. You'll see later that having these operators will already take care of the statistics part for you, meaning that your wave functions and stuff are going to be correctly anti-symmetrized. But then we need to also incorporate the quantum mechanics part, right? And those things are encoded in wave functions. So the idea now is just to attach, just to put them together. So these wave function operators between the statistics part and the quantum mechanics part. So you define this, you turn this, originally we used a phi of r, something like this, for the wave function. Right? So now we turn this into an operator by putting a hat here, and then remember we started with a complete, for the Fock state representation, we started with an operator that had a complete eigenbasis of one particle states, right? And we can have, for each of these n cat, we can have this spatial representation corresponding to some eigenfunction of the A operator, right? So let's use that. So sigma n, okay. We attach the annihilation operator corresponding to the n state with the eigenfunction psi n of r. Okay. So now, before we interpret these wave function operators, let's derive their commutation relations. What I mean is, oh no. Before we do that, let's think about the action of these commutation relations. So this is a commutation relation that operates. This is a wave function operator that operates on this one position, right? So I'm going to tell you that it's going to detect if there's a particle at that position, and it's going to pick out the wave function of the particle. So let me show you that by operating this on a one particle state. One particle state written in the Fock representation, which is, let's say the state is M. In terms of creation operators, this is what? This is B dagger M operating on the vacuum state. You guys, by now, you should understand the concept of the vacuum state.
You want to say something more about your phi sub n?
Oh.
Are they phi sub n?
So in our familiar thinking of direct notation, I said that we had the n bases there. So the phi sub n are just this represented on the coordinate basis, and we would like them to be normalized on that. All right, so let's see what happens when we operate the wave function operator onto a single particle state. So now, writing everything out. Okay, so I can just move these two freely because I simply just attach them together. These two don't talk to each other. Okay. So now, but this annihilation operator is going to see this creation operator, and we're going to use the anti-commutation relation, take this across, and then the annihilation operator is going to annihilate the vacuum, giving you 0. Right? And the anti-commutator gives you whatever is left. Right? So we can use this commutation relation, right? And replace this with replace this factor with the identity times delta nm minus correct? Does everybody follow this? I'm just using this. So I write this out and I move one factor to over here so we can acquire a minus sign. Okay. So now when the Bn, when this annihilation operator sees the vacuum, it's going to destroy it. Right? So I can throw away this term. Okay. And then over here I have a Kronecker delta function which I can use to remove this summation over n here. Okay. So I remove the summation over n, all that's left is the m's eigenfunction, right? Okay, so this is a bit uncomfortable because we have left the vacuum state attached. So actually, to get the wave function operator from the wave function operator and the Fox Fox state, we need to extract the wave function. We need to construct things like this. Okay, we use the vacuum state to test it. This is equal to phi m. Okay, so this takes out the particle at the position given by the coordinate r, and it takes out its eigenstate. Right? Okay. So in a sense, this wave function operator detects whether a particle is present at the position r. Right? Okay. So now we can, of course, construct this adjoint, this Hermitian conjugate. Now let's think about how the staggered wave function operator and this commutes. And we're going to use different positions. Are there any questions so far? No? So let's consider the product of this form, R prime, with a wave function operator at R. Okay, so just writing out the product explicitly, we have, let's use 2 index less than m. So we have B, okay, let me write this with more care, because the order of the operator matters. So let's change this to the one with m. So Bm dagger by m. Alright. And the other one with n. Correct? Okay, now these functions can be freely moved around, but we just need to respect the order of these operators. So combining the summation, we have correct? Okay. So now let's use the commutation relation again. We change this into 2 terms. You have the identity coming attached with a delta mn, subtracting the other term with their order reversed. Alright. Okay. So this term is going to remove one of these summations. So we have the identity operator attached with now just the summation over n. And then it's phi conjugate R prime, sorry. I forgot the prime thing. So that's the first term. And the second term is minus summation over m and n by m conjugate R prime by n R. So obviously this is just these two with their orders reversed, right? So this is just phi correct? Okay. What about this? Well, over here we're going to use the the direct notation and remove a identity operator. I mean, the identity operator is here, but we're going to use a completeness relation here. So turning this into direct notation, we can write this as phi n r prime. This as r phi n, correct? Okay. So now if I switch the order of this, and I look at this summation over n, what I get is, okay, let me not use phi n. Let me just use the n as we have defined it. Right? So we have the identity attached to sigma n r n r prime, correct? Okay. So what is this? This is the identity, right? So I can remove it, and now this cross these directly is cat, and that gives me a direct delta function, right? Because the different positions are normalized like that. So this term turns into a delta r minus r prime, right? And of course you attach this term, which is minus r. Right? Okay. So eventually, we can do that. The two wave function operators operating at different positions. And can anybody see the one from there? Is the light here? Maybe I can't see. Okay. Is this better? Yeah. All right. So I was saying we get that the anti-commutator again. Okay. All right. So now.
Really good to look at the I there, I hat.
Oh.
The left hand side is an operator, right?
Yeah, that's true. All right. So now we can also derive the commutation or anti-commutation relations between these operators and its Hermitian conjugate, which is the operator. Okay. So without doing it, let's think about what's going to happen. Let's think about what's going to happen. Suppose I had a dagger here. All that changes is if I had a dagger here, this goes to this. Right. So this is conjugated. Okay. So now, using the commutation relation, if I want to switch the order of these two, I just add a minus sign. So once I add the minus sign, I can break them up into the product of two wave function operators, and I'm done. So this one must be 0, and so is this 0. Because when you switch the terms, there's a minus sign, and when you construct the sum, of course it's 0. So that's how the wave function operates. Now let's turn to an interpretation of the wave function operators. And we do that by considering the operator that counts the total number of particles present in the Fock space. So I can construct an operator which represents the total number, so I use this n hat here. Okay, total. Now in terms of the creation and annihilation operators, we know that I just want to test sum over all of the possible states, okay, and test that if there is a state present there. Okay. So what do I do? If I'm given some state in the Fock representation, I try to annihilate the ith state and create it again, so that states without the I will be annihilated go to 0, it doesn't contribute. And whenever the I state is occupied, I get a 1. Right? So this obviously counts the total number. Right? So now, is there some way to represent this using the wave function operators? Yes, there is. And it's actually quite intuitive because if we look at our definition over here, okay, if we look at the definition over here, then what are we doing exactly? This is, if we forget about these hat, okay, so let me write it over here explicitly. So the definition of the wave function operators are these. So if we forget about these hat for now, then what does this look like to you? This is just an expansion onto an eigen, orthonormal eigenbasis. So this is some kind of Fourier synthesis equation, formula. Right, so this is Fourier synthesis. So the program of second quantization is I pick a state, I pick an operator, some observable, which has a complete orthonormal basis, these things. Right? I expand the wave function onto them, and then I turn the expansion coefficients into operators obeying the Fermi direct statistics. Right? So that's the whole program of second quantization in the fermion case. We can reverse this. Okay, let's attach the operators now. Okay. So let's do a Fourier analysis of both sides. Right? So to pick out the Bn over here, this operator, what do? We multiply by the conjugate of this, and then we integrate.